Hello class, welcome to Specialist 3-4. You're on for quite a journey. We're starting with vectors, so exercise 2A, introduction to vectors. Now, I'm pretty sure that this will be revision for most of you, so I'm quite happy for you to skip over the video as fast as you want to. You can use the right arrow, you can put it on speed ×2, whatever works for you, okay? But the first part we're going to cover is properties of vectors, vectors in geometry, operations on vectors, linear dependence and independence is part 2. So there's all these different examples and they relate directly to these questions, and you can see it in your textbook questions. You don't have to do each part of question 1, 2 and 3, but you need to come to class ready to go and having had a go to the point where either you do or you don't understand that question. And if you do understand it, we will push you harder in class. If you don't, we're going to make sure that you do get it. Okay. All right. So part 1, hopefully revision. So for those, well, definitely for those who've completed units 1 and 2. So a vector is defined basically as just a length and a direction. Okay. So all these ones you can see here in the first picture, these are all the same vector. Okay, so they've got the same direction and the same length. So they move in the same direction, same length. And you can represent them as column vectors. Okay, so in this case, if we're focusing on our x and y components, then this one moves 3 in the x and 2 in the y. And if you go back to the other ones, that's exactly what they means by being the same, is that from the start to the tip, you would move the same distance in the x, where's my mouse? The same distance in the x direction and y direction for all of those. Okay, and you can represent it as that. So for that one up there, we can say A to B and put an arrow above it to say it's that vector, but also you could just call it 3, 2. It's also worth noting that components can be negative. Okay, so for example, if this one here is minus AB, which is also known as BA, but if we had C and D, that was sort of the same thing, and this one here you can see it goes from D to C, so it moves in the negative direction for the X and up in the positive direction for Y. And this one here, it would move, well, it's opposite, isn't it? So it's 3 minus 2. Okay, and the other thing is for our notation, in the books they write it as bold, but I'm going to do this in my handwriting, okay, because there's no bold in my handwriting. So, what was I going to say? If there were 2 other points, E and F, where EF equals 3, 2, then EF equals AB equals V, this vector, okay? So basically, that's back to the initial thing where they're the same, is that we're just concerned about how much does this vector move and what direction, and then when we put them into these columns, it's just using the axes or components that we're talking about, okay? And also, it should be obvious that if AB was equal to U, then BA is equal to minus U. So magnitude of vectors, it's the length of the vectors, okay? So once again, no prizes for working out that Pythagoras is in play. And so using vectors above, the magnitude, and that's what obviously the size of, takes you back to modulus function, which I know you covered last year, is equal to 1 component squared, well, all the components squared, added together, and then take the square root of that. Okay, so for AB, the magnitude is 13. And BA, even though it's all negatives, it still ends up being the same magnitude. Adding vectors, there's 2 ways. You can add the column vectors I'll talk about in a second, but also it's really helpful if you can think about them as adding them geometrically, okay? So let this U equal this pink one, which I've copied a couple of times, and v equals the blue one, then we could rewrite, let's move this one here, okay, and we'll move this one here to be in the appropriate spot. Okay, and so now this new vector here is, if my pen wants to draw, that is, this new vector here is u plus v. Okay, and similarly, if I was to draw v plus u, then it would be this one. Okay, and it should be the same as the other one. I can't guarantee you that with my drawing, but it is. Okay, so let me move them together, and sure enough, that should tell you that u plus v is always going to be equal to v plus u. Okay, and let me just get rid of that. What are you doing? Okay, so you can also add them as column vectors, like I was saying before. So u plus, if this was u and v, so u is equal to 4, 1, and v is equal to -1, 3. If you add them together, you just add each component, the same way you add vectors or matrices, whichever way you want to talk about it. And so the 4 and the -1 add, the 1 and the 3 add, and we have our new vector here. Okay, so this u plus v, you can see it in the picture here, is moving across 3 and up 4, whereas u moves across 4 and up 1, and v moves up 3 but backwards 1. Okay, so it ends up being the same. Scalar multiplication, it's easy to understand when you think about the column vectors, but also geometrically, I've got this u here. This is supposed to be 3, 2. I hope it looks like that. So minus is the same vector going in the opposite, well, it is sort of the same vector going in the opposite direction. 2 times it is sort of the same vector again, but 2 times as long, and you can see it with the column matrix there. And half, you can scale it by a smaller number. Okay, so in fact you can scale these by any real number. And subtracting vectors, so if we were to consider u minus v from these vectors, we can think geometrically as u plus minus v. Okay, and what is really important, well, this is really important for this exercise, is that if I am thinking of this one here, okay, so u minus v, so if I could also look at this, if I take this over here, I'm going to take this thing here, so this will be my origin, and this is my A, and this is my B. Okay, because this thing, if I was going to look at it from the other way, if I didn't look at this as a plus, I'm going to see that if I O to A and plus A to B brings me back to O to B, right? So I can use this principle here to see that A to B is equal to O to B take away O to A. Okay, but that's just using these subtraction principles we've used already. It's much easier to think about these when we think about column vectors. Okay, So you can just add and subtract. You can subtract them in the same way you add. The zero vector is important. Okay, it's a really important concept. It's from scalar multiplication. We just multiply a vector by 0. It's just a point. Okay, and so it has no length and it has no direction. It's also an additive identity. Okay, so if I add the 0 vector to any other vector, it doesn't change, and that means there's an inverse, which is its own negative value. So a plus minus a is equal to the 0 vector. Okay, and it also means that any point to itself, the vector is a 0 vector. So you don't go in any direction and you don't travel any distance to stay where you are, in other words. We can use vectors to represent the edges of polygons. So it's going to be a really useful way of looking at things like that. And at the end of this chapter, we're going to do some proofs based on these facts. Okay, so let's have a look at AB and BC. Then AB plus BC equals AC. Okay, because A to B plus B to C equals A to C. Okay, and that's sort of, we're going to use that same principle again. Okay, so that means that B to C is going to equal AC, and I just have to subtract the A to B over to the other side, and that's what B to C equals. Okay. And also, if we have the polygons where they all continually travel around, it seems to be like following the same path, in the end you end up with A to A, which is the 0 vector. Okay, the example in the book had eight-sided gon. All right, so I have done these examples in separate videos, so I won't spend much time on them now. Just the point of this one is that you can drag a vector around anywhere and it's still the same vector. And this was obviously discussed earlier in the exercise. And I made a point, I did something on GeoGebra so you could see that it didn't matter where it was. We travel 3 in the X direction and down 2 in the Y direction. So that's the same vector. Finding the points, well, you would just subtract the values. Okay, so from here to here is, so another way I could have written that was whatever this vector is, 2, 6, plus that vector, if it's going to let me write. So 2, 6 plus A, B will equal 3, 1. Okay, and so I just subtract the 2, 6, and that will give us the answer we want, okay, which is 1 minus 5. And this is just showing that if I adding along these vectors, it's A to D is going to be just the sum of all those vectors, okay? Because A goes to B and B goes to C and C goes to D, and we've gone from A to D. So you can write that as this direct vector. It doesn't matter that all these paths have happened in the meantime. When we look at it as a vector, we look at it as this straight initial vector. Parallel vectors, well, that goes back very much to our scalar multiplication, okay? So I should mention that here. It's sort of same idea as scalar. There's a real problem with this pen at the moment, multiplication. And position vectors, okay? So you can think of points as a vector from the origin to that point. And that really, there's some maths well, you guys have already seen complex numbers. Complex numbers you can think of as vectors in space as well. And these are really useful concepts for lots of mathematical concepts and applications in life. Vectors in 3D, no big deal. Okay, that's exactly the same as vectors in 2D. We just have an extra value. Okay, and so here is the picture from the textbook. When I say they're no big deal, they're a big deal to draw sometimes, but as far as mathematics goes, they're pretty straightforward. In fact, you can have vectors in as many dimensions as you want. Okay, and you can even have something like a Hilbert space, which is in infinite dimensions. So, but at this point in time, you just worry about the 2 and the 3 dimensions, and a vector is just how much do you travel in relation to each axis, okay? So the A1 value there is how much have I moved down the x-axis, and same for A2 on the y, and A3 is now the z. And don't forget, of course, they could also be negative, to be in a different, it's not a quadrant, but whatever you call them in 3D space. This is copied out of the textbook. These are little facts I'm sure you could pick up, but that's just a formal way of discussing it, okay? Commutative, associative, zero vector, which means there's an additive and inverse, and the distributive law is just for, we're talking about the real number here, not another vector multiplying through, okay? And the other thing to remember is that this is vectors v to an because we have the A1 here and the A1 there, okay? So that because they're all sort of connected like a chain in that way, so on and so forth, that's why we end up from V to AN. If we had some reason they had a different thing in there, that's not the case. But we're looking at the vector that circumvents this long journey, okay? This one here I think should be pretty straightforward for most of you, just knowing that it's a cuboid. So I've coloured in to know which vectors are which. So we're renaming our point O to A as being a vector of having these properties as a vector. It doesn't matter that we don't know what they are, we just do the algebra for them, okay? And this was using a midpoint, so understanding that, for example, n is half of O to C. O to n is half of O to C, and same for n to C as well, okay? And there's a really important fact here that captured in part B about this midpoint here, okay, M, because we knew what A and, well, excuse me, green is A and yellow is C, so we know that M is the middle of them, and it's actually equal to what looks like the average of those two vectors. Okay, really important fact. Once again, here we're using this fact once again, okay? So origin to n, origin to m. M to n is equal to origin to the one we end up at, so n in this case, minus the minus the other one, okay? So origin to n, if I use this here, let me write that again. So it makes more sense if I write it out this way, okay? So O to n is equal to O to m plus m to n. So that means m to n is, if I subtract this O to m off both sides, oh God. Anyhow, I'm not gonna fight with this pen right now. Okay, so O to m. So the n vector subtract the start vector. Okay, gives you the vector between the two. Linear dependence and independence, very important fact. Okay. It's a lot to do with things like simultaneous equations and that. So it's worth pointing out that having a third vector in two-dimensional space, being able, it being a makeup of the other two vectors, of scales of the other two vectors, is not surprising. Okay, it's really not. So the point is that K and L in this example are real numbers. Okay, and A and B are the other vectors. And to say that they're parallel to one another is just a little bit of algebra here, and you can see that that just means that A is equal to minus L times K. So if they're parallel, there's somehow some sort of scalar going on here. So A is just equal to some scale of B. So they're on the same line. Three vectors are linear dependent if you've got the three real numbers here multiplied by each one of them, and they then become the zero vector. And you can imagine that if I subtracted B and LB and MC on the other side, divide everything by K, then K is equal to minus L, so A is equal to minus L times, well, anyhow, you can just see, you can, I wanted to draw this on, but the pen is giving me such a hard time that if I could end up doing, will it do it? Oh, it will. So minus L on K times B minus M on K times C. So it will also work out that, anyhow. So, but that is quite interesting, and I'll show you why in class. Why, if that happens, what else might be going on. Okay, but as I said, it should be obvious to you that if I have two-dimensional vectors, okay, so this is 2D here, that I could stretch each one of these, stretch or shrink, and make any point on this surface by doing that. And I've got, as I said, I've got an applet to demonstrate that. As I said, there's something interesting going on when we have a 3D linear dependence, okay, between the three of them. I was going to say, is my pen going to let me do this? It won't let me do this, so I should have done it earlier. But we can talk about this one in class. I'll put that in the notes, so we'll talk about that in class, why M has to be equal to P and N. Oh, I think I can do that. So, come on, pen. Yes, you're going to work. All right, so the reason why this has to be true is that, where is it? How long is this going on for? Let me just check. All right, so yeah, we're taking up a lot of time here, but all we have to do here is just simple algebra to show why this is true, okay? So if I now subtract M A plus N B, and if I subtract the other one over, we're going to have minus PA. No, it's not going to let me do it. We'll do this in class. But basically, if you realize that A and B are linearly independent themselves, you'll see why. Okay, maybe you can do that yourself. I'll check that in class. Here's some examples. These are quite hard. Well, the first one's not. Example 6 is not. It's just some simultaneous equations. But example 7 requires a little bit more thinking, a little bit of a challenge, and your question for that in the exercise is, let me check where that is, in questions 16 and 17. So you definitely want to try those out, okay? But yeah, I've got a separate video of me doing these examples, so it's probably best that you go through them. But in the end, I used that triangle rule, okay? And I used where there was some sort of scale, and then we're left with a simple like simultaneous type question. All right, so apologies about my pen, and also this is a long exercise, so hopefully the videos don't take this long for the rest of the year. All right, have fun.